So the components we have seen so far, they all had two states, failed or operational. But we also have three-state components, which means they have an operational state where everything's working well. They have a short failure or failed close. They also have an failed open or open failure. But what do these mean? So consider a switch in a circuit. The purpose of the switch is to connect these two nodes. So you can close it, you can open it. Once it's closed, the circuit is also closed. So the electricity goes from the battery to a light bulb and turns it on. When we say the switch has failed short or closed, it means it has failed in the closed state. Therefore, the light bulb is always on until the battery is drained. And when we say it fails open, it means we're not able to close it back to get the current go from the battery to the lamp. Or it could be, in this is, we could physically close it, but the material here could be defective and we would never have we would think of this circuit as an open circuit in that case. We would call this a closed circuit. A closed circuit is one that lets the current flow from the battery, electricity go from battery to the light bulb. Other examples are valves that let the water flow through the valve to other parts of the system. If you're thinking of only one of these switches, it's easy to incorporate the reliability into the reliability of the system because these two are just failure modes, and we can assign a probability to both of them, and this could be the operational, so it becomes like the normal two-state device, a two-state device. But when they are put into a series or parallel configuration or a structure, then they cause some problems, and it's not as easy to calculate the reliability of the system. So let's see. First, I'm going to talk about series structure. So let's look at the circuit that has two switches in series. In first case, one of the switches fails short. What does that mean? So you have two switches. We're going to put two switches here, one battery, one light bulb, another switch here. Okay. One of them is functional, so you can open close it. The other one is failed short or failed close. In that case, you still have control. So although this one has failed and this one is working, the entire circuit still works or is operational because you have control over the circuit by that one switch that is left. Okay, but what if both switches fail short? So in that case, there is no way you could open the circuit and this lamp or this light bulb will be always on until this battery is drained. So we don't have any control over the system, and we would say the system has failed or is not functional. The third case, one of them fails open. How does that one look? So the first one is functional. This one is failed open, which means it's the stuck and doesn't let the electricity go through that point. So in that case, the system is not operational because it doesn't matter if this one switch, this operational one switch number 2 is open or closed. You can't have the current, you can't have the electricity go through the first switch. So the circuit will be always open. And if both fail open, it's even worse, right? Because now you have 2 points that are open. All right, so Q, which is the failure of the entire circuit, happens when, look at these, number 2, number 3, and number 4. Number 2 is when both fail short, or one of them, one or both, I would say at least one fails open. So in series structure with 3-state components, that is when the entire circuit or entire system fails. Okay, I can consider this one event, call it E1, and I can consider this another event, call it E2. So probability of Q is basically, Q is basically the probability of E1 or, again, made a mistake, which is okay. So for OR, we use the union. Probability that either of these two happen. So reliability would be 1 minus that. Because reliability is always equal to 1 minus failure. Both of them are probabilities, and they're complements. So let's define QOI, probability that component I fails open, and QSI, probability that component I fails short. All right. From there, what is Q? Q is P of E1, E2. I can rewrite that as P of E1 plus P of E2, and P of E1 itself was both fell short. So first one fell short and second one fell short. QS1 times QS2 plus at least one of them fails open, which is basically the union of QO1, QO2. And I can rewrite that as QO1 plus QO2 minus QO1, QO2. basic probability. Because those two events are independent, I have to subtract their joint probability. Okay, so if I do the math and I rewrite reliability as 1 minus Q, I get to this point. 1 minus Q O1 times 1 minus Q O2 minus QS1 QS2. That is what I'm looking for. Reliability is basically the probability that neither of them fails open, none of them fails open. This first one, this one means first switch doesn't fail open. This one means switch 2 doesn't fail open. And the product of them means neither of them fails open, minus the probability that both of them fail short. So reliability of the system is probability that both neither actually none of them fail open minus the probability that both fail short. And I want to generalize that and write if you have n components instead of 2 in series, I want to write 1 minus Q or I minus all of them fail short. Product of QSI. Okay, that was the series structure. So probability that none of them fails open minus the probability that all of them fail short. Okay, let's just memorize or remember this part, this last part, the blue one. Probability that all fail short, none of them fails open minus the probability that all of them fail short. So now let's look at the parallel structure. So I will write parallel. Those two switches are now in parallel, which looks like you have one switch here, and in parallel you have another switch. And these two are located in a circuit that has a battery and a light bulb. And if both of them are open, of course, you don't get the electricity going from the battery to the lamp, and it won't be on. You won't be able to turn it on. And if you close one of them, only one of them, the circuit will be closed because the electricity goes through one of those two switches, and the lamp will be on. So let's look at some cases. One is one of them fails open, which means, for example, this one is stuck like that. You cannot close it back. So because you have the other switch, through the other switch you have control over the circuit. You can open or close that one and turn on or off the lamp or the light bulb. So in this case, although component number 2 has failed, because this one works, the entire system also is operational. So next case, both fail open. Both of them fail open. So this one is stuck, this one is stuck. You cannot close it back. So this part of the system is always open. You can't have a closed circuit, so the entire system is non-functional. Next case, one of them fails short. How does that one look? So one of them is functional, you can close it back, you can open it, but the other one is stuck like that. So because the other one is stuck like that or has failed short, failed closed, you will always have the current go through the second one, which is failed. And that way, the battery will be always on. I mean, the light bulb will be always on until the battery is drained. And next case, both fail short. In that case, it's even worse. Again, it's always closed. The circuit is always closed. You cannot open it. You cannot turn it off. It's always on until the battery is gone. So in both of these cases, we would say that the system has failed. So let's summarize it. What do we see here? Case number 1, case number 2, 3, and 4. In these, we can see that the system fails when, as in number 2, both of them fail open, or, as in 3 and 4, at least one of them fails short. So both of them fail open, or at least one fails closed or short. I'm going to call that E1 and I'm going to call that E2. Therefore, Q is probability of E1 or E2 equal to probability of E1 plus probability of E2, which is, so what is the first one? Probability that both of them fail open. QO1 and QO2 plus QS1 plus QS2 minus joint probability QS1, QS2. And we know that reliability is 1 minus Q. And if we, which is basically 1 minus what we have up here, QO1, QO2 plus QS1, QS2. If we continue that, we get to this point. 1 minus QS1, 1 minus QS2 minus QO1, QO2. This is what we want. And let's generalize that like we did before for the series structure. I would write reliability of the system is the probability that all of them, none of them fails short, because we can see if any of them fails short, the entire system will be failed, will be always closed circuit. So the probability that none of them fail short, first one doesn't fail short and second one doesn't fail short, so it's a product of them. I want to N 1 minus Q SI minus the probability that all of them fail open, QOI. All right. So let's only keep that one in mind. So in summary, in series structure, reliability of the system is the probability that none of them fails open minus the probability that all of them fail short. And in parallel, it's just the opposite. Probability that all of them fail closed minus the probability that, probability that none of them fails short minus the probability that all of them fail open. Let's look at an example. A mechanical valve fails open 5% of the time. So QO is 5%. And it fails short 10% of the time. So QS is 0.10. Compute the system reliability for 3 valves, 1 in series, 2 in parallel. So we have 3 of those. First in series. What was it for series? It was the probability that none of them fails open minus all of them fail short. So 1 minus QO times 3, because we have 3 of them. First one doesn't fail open, and second one doesn't fail open, and third one doesn't fail open. Because there is and between them, it's the product of them. So it's the power of 3 minus probability that all of them fail short. First one fails short, and second one fails short, and third one fails short. That gives me 1 minus 5% to the power of 3 minus that to the power of 3, and that is 0.856. And in parallel, reliability of the system is none of them fails short minus just the opposite of the other one, minus the probability that all of them fail open. So 1 minus QS, 3 minus QO3, 1 minus 0.10 minus 0.05 to the power of 3, and that gives me 0.729. You can see that in this case, the parallel structure, interestingly enough, has a lower probability than the series structure. So previously we have seen that series structure always brings down the reliability, and parallel increases it. But for three-state devices, three-state components, that is not the case. Also, we saw previously that low-level redundancy increases the reliability compared to a high-level redundancy. So we saw that for two-state devices, reliability of low-level redundancy was higher than the reliability of high-level redundancy. But let's see how that one changes for three-state components. So in general, if our base system is composed of a bunch of components, M components in series, when we say we have a low-level redundancy, it means I'm copying or duplicating each component several times and put n of these in parallel. So this is a low-level redundancy structure. Low level. A high level redundancy So this was our original system, 1, 2, M, and we copy or duplicate the entire system, not individual components. So I'm gonna have another one of these in parallel with the original. 1, 2, M, and we have N of these here, and we have N of these here. Okay, but the question is, how do we get how do we calculate the reliability of the system in these two low level and high level redundancy structures? To make that simple or simplify it, let's call these X's, and let's call these, sorry, go back. Let's call these Y's. Here you can see that these X's, X1 through XM, are in series, and here you can see that these Y's that are identical are in parallel. So from what we talked about previously, we know that reliability of the system in series structure was none of them fails open minus all of them fail short. None fails open minus all fail short. So none of those X's should fail open. How many of those X's do I have? N of those. All right. Sorry, I have M of those. I goes from 1 to M. None of them should fail open. But if you look at it, we have N of those in parallel. So for that X to fail open, I need all of them to fail open. Otherwise, the current will go through that one that is still closed or can be closed. So all of those M's, all of those twos, all of those ones, all of those I's should fail for that part, for that X part, to fail open. So I'm going to multiply that by N, which means all of them should fail. And 1 minus that means that that X will not fail open. And I want none of those to fail open. None of these X's. So if this is X and this is X1, I want none of the X's fail open. Minus the probability that all of them fail short. So all of the, I have M of those. I goes from 1 to M. None of them fail short. So how do those fail short? Sorry, minus the probability that all of them fail short. So what is the probability that each one of those X's fails short? If any of those fails short because they are in parallel, the entire block, the entire X will fail short. Because of that, I would write one minus Q SI N. So look at it. This part, this green part, means this green part including this N, means none fails short. None of them fail short. And 1 minus that, which is this part, means at least one fails short. Okay. If at least one of these components within each x fails short, then that x fails short. Okay. And that's what we're looking for. Here we say all of them fail short. So that's the probability that the first x fails short. All right, let's move to the parallel structure. Parallel structure, the reliability of the system. In parallel, we know that. Let me start a little higher to have enough space. Reliability of the system is none of these y's fails short minus all fail open. None of them fail short minus the probability that all of them fail open. Now, what is the probability that, first of all, how many of these y's do I have? And they are very identical. I want none of these y's to fail short. And I have n of those. So first one doesn't fail short, second one doesn't fail short, and third one, and fourth one, and nth one. I have n of those. They don't fail short. 1 minus I goes from 1 to m QSI. Again, product of QSIs means that all of them fail short. And 1 minus that is at least one fails short. That to the power of n because we have n of these in parallel. Minus all of them fail open. 1 minus product of y equals 1 to m q o I n. So what is this n is for that entire thing. So I have n of these. If I say all of them fail open, first one fails open, and second one fails open, and third one fails open. So it's n of these events, and I want all of them to happen. So this whole thing is to the power of n. This whole thing is to the power of n. Within parentheses, I have the probability that each y fails open. For each y to fail open, I need at least one of those to fail open. So this is the probability that at least one fails open. Within that series structure, if at least one of them fails open, that entire y fails open. And for that, I write 1 minus the probability that none of them fails open. None fails open. 1 minus probability that none of them fails open is the probability that at least one of them fails open. If at least one of those is open, that y fails open. And I have n of those y's. So that whole thing to the power of n gives me the probability that all fail open. What I was looking for here. And the first statement just tells me the probability that none of them fails short. So first y doesn't fail short, and second one doesn't fail short, and third one doesn't fail short. So I have n of those. And again, if at least So for that entire Y to fail short, I need all of them to fail short. So if all of them fail short, uh, sorry, 1 minus that circle that I just drew is the probability that, so this probability that at least one fails short. If at least one of them fails short, then, sorry, I made a mistake here. This circle tells you the probability that all of them fail short. And this Y fails short when all of them fail short. And 1 minus that is the probability that at least one of them doesn't fail short. And if that's the case, we have control over that series structure, and that part doesn't fail short. Okay? So we want at least one of them to not fail short. Okay, this entire high level, low level redundancy became a little complex maybe, but the most important parts are these two that we previously covered. Parallel structure and series structure. So for two-state components, we saw that reliability of low level was higher than the reliability of high level. Now let's look at an example. We have three components, each has a different short failure and open failure probability. As you can see here, for example, number one, 15% probability of short failure, 5% probability of open failure. And if we follow the formulas that we just went over, we see that reliability of low-level redundancy is 0.97 and reliability of high-level redundancy is 0.98, which shows that here in this case, it's not always the case, but in this case, reliability of high level is greater than reliability of low level, which wasn't the case for two-state components. All right, that's all I had for three-state components.